Good morning. Welcome to the session for Management of Machines and Materials, MMPC009. Today we will be discussing about Unit 5, 6, and 7. Earlier we have already started Unit 5, that was Planning and Control for Mass Production. Under that, today we'll start with Designing of an Assembly Line. The work elements which have been established through the division of labor principle are assigned to the workstations so that all stations have nearly equal amount of work to do. Each worker at his or her station is assigned certain of the work elements. The worker performs them repeatedly on each production unit as it passes the station. The assembly line balancing problem is generally one of minimizing the total amount, ideal time, or equivalently minimizing the number of operators to do a given amount of work at a given assembly line speed. This is known as minimizing the balance delay. Now, what is meant by balance delay? It is defined as the amount of ideal time for the entire assembly line as a fraction of total working time resulting from unequal task time assigned to various stations. After studying the variation in ideal times at stations caused by different assembly lines, balances concluded that high balance delay for an assembly line system for a specific product is caused by wide range of work element times. Number two, a large amount of inflexible line mechanization and indiscriminate choice of cycle types. Moving, what is how this division of work into part is done, is calculated, is designed. This is done with the help of precedence diagram. The total job to be done on the assembly is divided into work elements. The diagram that describes the order in which work elements should be performed is called a precedence diagram. This figure shows the precision diagram for an assembly with 12 work elements. You can see how these 12 work elements are placed. Yeah, we see that 2 and 4, task number 2 and 4, cannot start or begin until this task 1 is completed. Moreover, there is no restriction on whether task 2 is done first or task 4 is done. These two tasks are unrelated, meaning thereby that they may be done in parallel or even with partial overlap. A task may well have more than one immediate procedure. For example, in the precision diagram figure, task 12 has three immediate procedures and cannot begin until all these three work elements, that is 8, 9, and 11, are completed. Now, grouping of tasks for workstations and efficiency criteria. Depending on the desired production rate of the line, the cycle time, we call it as CT, or the time between the completion of two successive assemblies can be determined. This determines the conveyor speed in the assembly line or the time allocated to each operator to complete his share of work in a manual line. The individual work elements or tasks are then grouped into workstations such that number one, the station time ST, which is the sum of the times of work elements performed at that station and should not exceed the cycle time. The precedence restriction implied by the precision diagrams are not violated. There are many possible ways to group these tasks, keeping the above restrictions in mind. And we often use criteria like line efficiency, balance delay, and smoothness index to measure how good or bad a particular grouping is. Line balancing methods. First and most widely used method is Kilbridge and Webster method. They propose that numbers are designed to each operation describing how many procedures it has. Operation with the lowest procedure number are assigned work to the workstation. The procedure consists of the following steps. Number one, construct the precision diagram for the work elements. In the precision diagram, list in column 1 all work elements that need not follow others. Column 2, list work elements that must follow those in column 1. Continue to other columns in such way. Second criteria is to select a feasible cycle time, that is CT. And this is done by, we can keep this criteria into consideration that the T total time maximum should be less than cycle time, and cycle time should be less than all the summation of the intermediate procedure elements. Assign work elements to the station such that the sum of elemental time does not exceed the cycle time. This assignment proceeds from column 1 to 2 and so on, breaking intra-column ties using the criteria of minimum number of procedures. Delete the assigned elements from the total number of work elements and repeat step 3. If the station time exceeds the cycle time due to the inclusion of a certain work element, this work element should be assigned to the next station. Then we have to repeat step 3 to 5 until all assigned to the workstations. Now, we will discuss this method, or we will find it out which is the best possible combination to perform these activities. We have to design an assembly line for a cycle time of 10 minutes for the following 12 elements, and we have to use Gilbert-Wester method. This data is given to us. First of all, we will convert this diagram into precedence diagram. The grouping initially, as per the information provided to us over here, is transformed into the precision diagram. We have drawn this diagram starting from 1, 2, 3, 4, 5, 6, 7, 8, 12, 6, 9, 12, and 6, 10, 11, 12. There are 7 stations. Now, how the calculation of the work is done, what we have discussed, for the different methods we have discussed earlier. Column 1, these are the 7 stations. Column 2 consists of the elements in these stations. Column 3 is specifying the time allotted to complete that particular element. And column 4 is the total sum time of that particular workstation. And column 5 is the ideal time. After calculating all these, we find that the ideal time for station 1 is 5, station 2 is 4, station 3 is 0, and 4, 5, station 5 it is 3, station 6 0, and station 7 it is 3. The total time of the procedure assembly comes out to be 50 minutes. Now we have to calculate line efficiency, which is sum of all the times of various work elements upon total number of workstations into cycle time. So there is the total sum of the station time was 50, which is given in the problem. Total number of workstations what we have designed is 7, and the total cycle time is 10. That's into it has to be multiplied by 100, which comes out to be 71.4. Line efficiency is not satisfactory. Then comes your balance delay. Total time was 100 minus 71.43 what we have calculated, and the delay comes out to be 28.57%, which is again a numerical number, too high. Then the third element what we have to calculate is the smoothness index. So we will be squaring the times of all the elements, and we will be taking the under root of it. It comes out to be 9.17. Again, numerically, it is too high. That means some modifications have to be done. Now, we will be reclubbing or regrouping the original problem into different combinations. So here we can see we have reduced the number of workstations from 7 to 6. The recurring is shown over here. So we will be drawing up the table again for this precedence diagram. This comes out to be like this. Group 1, the elements are 1 and 2, total time is 8, and ideal time is 2. We will be calculating all for all the 6 stations. This comes out to be 0 for station number 5. Now, similarly, we have to calculate the line efficiency. So this comes out to be, in this case, 83.33. The balance delay is now 16.67. This value is numerically lower what we have done earlier. And smoothness index is also a good number now. It is 4.89. From the above result, we have seen that there have been an improvement in the light efficiency from 71.43 to 83.3, an improvement of almost 11.9%. And also the value of balance delay and smoothness index have gone down considerably, which is a positive sign for line balancing. What are the problems and prospects of mass production variable work element types? In line balancing method, it is assumed that the work element times are constant. In practice, these times may be varying randomly owing to factors like human variability, fatigue, or carelessness on the operator's part. Even in case of machine operation, the setup of positioning time of the part or component could lead to random variations in the individual work element times. Since the assembly line is balanced for a given fixed set of work elements times, the effect of these variability is twofold. Number one, greater idle time at workstation and the reduction of the average production rate on the line. In designing lines for random work element times with given mean and variance, some modification of the deterministic ideal time balancing method is adopted, utilizing the additional criteria that the probability of the station time exceeding the cycle time should be kept low as possible. Modular production and group technology. Modular production system involves a group of 14 to 17 people who set their own standards and work together to produce a finished garment. Basically, it is started from the garment industry. They work as a team of module and each team member works on more than one operation. In this system, operators help each other to finish the garment quickly and the team is fully responsible for the production and quality. The number of teams in a plant varies with the need of the industry, size of the industry, and product line in the garments. This system, MPS, is the perfect solution for the apparel manufacturer where quick response is needed. This system is also popular as a cellular garment manufacturer, flexible work groups, or Toyota swing system, TSS. Here we can see that in this diagram, there are 9 machines and 4 operators. They are working together on different workstations as per the requirement and they are completing at the process. What are the advantages? MPS leads to cost saving. The system is highly flexible with style changes and permits better line balancing. Enables fast throughput time, lower WIP, and small batch size can be achieved. Peer pressure encourages a team spirit and discourages absenteeism. What are the features of a popular production system? Usually U-shaped layout with more workplaces than operators is used. Preferred, required multi-skilled workers and a small set of machines to produce a finished garment. Each operator performs approximately 2 to 4 operations depending upon the product. Workflow is sequential. WIP is less and productivity is high in this production system. The operators stand, sit at their stations and rotate in different sewing machines to complete the operations. Pull type production system, in which the job order arrives from the last step to previous step. Time spent per garment is also little. For example, for t-shirts, it's almost 3 minutes. Pull-on pants, 6 minutes. Unstructured jacket, 25 minutes. Linen blazers, 40 minutes. Tailored coat, 120 minutes. Moving further, it is group technology. First of all, the definition of group technology. It is an approach to organizing manufacturer which can be applied in any industry. It can be machining, welding, foundry, presswork, forging, plastic molding, etc., where small batch variety production is used. The basic approach enables all aspects of manufacturing from design through estimation and planning to production to be rationalized. Informs the basis for the development of computer aided procedures and flexible automation. What are the advantages of group technology? Better lead time results in fast response and more reliable delivery. Material handling is reduced considerably. Robots can be easily used for material handling. Better space utilization. A small variety of tools, jigs, and fixtures are required. If something has advantage, so it has disadvantage also. Additional cost of implementation of this system, rate of change in product range and mix is there, difficulties with out of cell operations, and coexistence with non-cellular systems. Then, as we have said, we have to take help of automation in mass production. The mass production has been assisted to a large extent by automation and robotics in the recent past. Automation refers generally to the bringing together of three basic building blocks: machine tools, material handling, and controls. Often a considerable amount of time is spent on to load machine and unload work and to convey it between the single operation machines. This restriction have been partly relieved by the development of multiple spindle machines. With this machine, a single motor driving several spindles through a gear train allows multiple operations to be performed by one machine. Machining cycle time does not change, but more machining operations can be performed within each cycle, and several machining operations can be performed on one machine by a single operator. Another trend with automation has been the use of industrial robots to perform some of the functions that were earlier done by manual operators. An industrial robot is defined by the Robot Institute of America is a programmable, multifunction manipulator designed to move material, parts, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. Industrial robot consists of three basic components: the manipulator, which is the arm, which is a series of mechanical linkages and joints capable of movement in various directions to perform the work task. Second one is the controller, which actually directs the movement and operations performed by the manipulator. The controller may be an integral part of the manipulator or may be housed in a separate cabinet. The third one is the power source, which provides energy to the actuators on the arm. The power source may be electrical, hydraulic, or pneumatic. Major reason for use of robots in industry are increased productivity adaptability, safety, ease of training, return on investment, and greater reliability. Robots are currently in operation in welding and assembly, drilling and routing, inspection, material handling, machine loading, die casting, and variety of other applications. We can see with this figure, robots are being used in car assembly lines at two different stations. Now we move on to Unit 6, which is related to planning and control of batch production. When a variety of product is to be made and the volume of productions are not large enough to justify a separate line for each product, production in batches is often resorted to. Batch production implies that general purpose machines are utilized for production of different products. Material flow tends to be more complex in such systems than in mass production systems. The layout plan for such systems has to be carefully designed, keeping in mind the diversity of products and their individual flow patterns and production volumes. Naturally, in such system of production times are larger as compared to those in mass production. Batch production is different from job shop as in batch production a continuous demand for certain product exists. But because the rate of production exceeds the rate of demand, there is a need to produce product in batches. The scheduling problem here is concerned with determining the batch size for products and the order in which they should be performed. What are the features of batch production? We will start with advantages. Better utilization of machine is possible. Consequently, fewer machines are required. A high degree of flexibility exists vis-a-vis equipment or manpower allocation for specific tasks. Comparatively, low investment in machine is needed. Generally, there is generally greater job satisfaction for the operator owing to the diversity of the job handled, and specialized supervision is possible. Disadvantage: since longer and irregular flow line results, material handling is more expensive. Production planning and control systems are more involved. Total production time is usually longer. Comparatively, large amount of in-process inventory results. Space and capital are tied up for work in progress. Because of the diversity of the job, a specialized department, high grade of skills are required. Then we move to material requirements planning. In short, we call it as MRP. A material requirements planning system is a planning and decision-making tool used in production process which analyzes current inventory level versus production capacity and the need to manufacture goods based on forecasts. MRP schedules production as per bills of material while minimizing inventory. The technique is computerized and looks at requirements within a fixed period. What are the main features of MRP system? A master production schedule, a statement of the planning including orders, forecast and capacity has to be planned. Bill of material, what we call it as BOM. All the material and components required to make the final product are listed. An inventory status file. This file is about stock record that allows cross requirement to be adjusted to net requirements. What are the basic steps of MRP? First one is determining the product type. Second one, calculating demand and setting volume. Identifying required raw material and components. Checking existing inventory levels. Examining the manufacturing capacity. Planning production. And scheduling delivery. What are the advantages of an MRP system? MRP, that is Material Requirements Planning System, is a planning tool It is basically used where the system is widely credited for playing a crucial part in decreasing factory inventory. It also exists in manufacturing industrial products that are more complex. MRP focus is on what materials are required and when they need to be sourced. It is also helpful in product customization. MRP has historically been seen as giving additional advantage because it is known to schedule and track every order, whether for production or purchase. Here we can see that how MRPs, what are the MRP steps and processes are. First of all, it is identifying requirements to meet demand. Second is checking inventory and allocating resources. Third one is scheduling production. And fourth one is identifying issues for making recommendations if required. How the comparison with the input for production, its objectives and benefits are there. If we talk about product type, keeping the material and components level as low as feasible. The benefits will be reduced inventory and overhead costs. Quantity and delivery, making raw materials readily available for production. And for that, the benefit will be improved production cycle. As far as inventory status is concerned, the objective here involved will be scheduling, manufacturing, distribution, and purchases. And we will have a sufficient stock to meet the demand. Stock shelf life, reduced lead times will be there. And as far as your bill of material is concerned, the customer satisfaction will be a benefit. Now we will be comparing MRP with ERP. ERP is Enterprise Resource Planning. MRP system focus specially on planning and controlling how goods are assembled using multiple raw materials or components by controlling inventory, componentry, and the manufacturing process. On the other hand, your enterprise resource planning system, that is what we call as ERP, system are an offshoot of MRP system, spurred by businesses finding a need for the same level of planning and oversight for some other operations such as payroll, finances, and supplier management. ERP systems plan for resources across the entire organization, including financial management, order management, customer relationship management, people, procurement, warehousing, and fulfillment. The line of balance for production control and monitoring, what we call it as LOB. LOB is a management control process for collecting, measuring, and presenting facts relating to time, cost, and accomplishment, all measured against a specific plan. In shows the process, status background, timing, and phasing of the project activities, thus providing management with measuring tools that help comparing actual progress with a formal objective plan, examining only the deviations from established plans and gauging their degree of severity with respect to the remainder of the project, receiving timely information concerning trouble areas and indicating areas where appropriate corrective action is required. Then, forecasting future performance. Purpose of line of balance. The purpose of LOB is to enable program manager to see it at a single glance which activities of the operation are in balance, that is, whether those which should have been completed at the time of the review actually are completed, and whether any activities scheduled for future completion are lagging behind schedule. LOB chart comprises only one feature of the whole philosophy, which includes numerous danger signals control for, for all the various levels of management concern. What are the benefits of LOB? A better understanding of the amount of work taking place at a certain time in a specific place. Optimized resources for a large number of repeated work activities. allows easier cost and time optimization analysis, easy to modify, update, and change the schedule, better management of subcontractors and resources, and identifies issues in advance. Developing a line of balance chart. What is included in? To do a LOB, the following is needed. A contract schedule or objective chart is made. A production plan or lead time chart for the production processes are depicted. Control points, cumulative inventories, and a program status chart on which to plot LOB and the cumulative quantities of units that have been passed through the control points of assembly or production process. What are the problems and prospects of batch production? In batch production system, the in-process inventories and the lead times tends to be large. As we have seen, MRP is a vehicle to control the discrete part production planning and also to reduce work in process inventory. However, the drawback of MRP is that it is expensive to implement as it requires the capability of a mainframe computer, technical support professionals, and MRP software. Instead of designing production control tools for a complex production system, attempts have been made to identify or to simplify the system itself. One example of this is Kanban, developed in Japan and is being implemented at Takahama plant of Toyota. Kanban emphasizes the reduction in production lead time and in process inventory by specifying shorter production runs of any single product. Another major development with respect to the complicated problems of batch manufacturing has been development of flexible manufacturing system, that is FMS. It is an attempt to apply computer controls to production scheduling. The control of machines and the movement of material in a discrete parts manufacturing environment. FMS may be defined as general purpose manufacturing machines, which are quite versatile and capable of performing different types of operations linked together by material handling systems. Both the machines and the material handling systems are under the control of a central computer system. There are two main objectives of employing FMS. It permits machining of any desired mix of parts in a given time period and to reduce the working process and increase machine utilization in small lot manufacturing. We move to Unit 7, that is planning and control for job shop production. As in mass production system, where a limited number of items are produced continuously without any change. The job shop characterizes a situation where a variety of jobs is handled, each job being different from the previous one. Job shop differs from batch production in the following manner. In batch production, there is generally a continuous demand for product, but owing to a higher rate of production as compared to the rate of demand. Production is undertaken in batches. Batch production caters to a predictable variety of jobs. Variety of problems in job production. A typical formulation of the job shop scheduling problem is given n jobs to be processed through m machines, each job having a predetermined sequence of operations and processing time. In what order should the jobs be loaded on the machines so as to optimize certain performance criteria? A typical list of performance criteria to be optimized is total processing time or make span, mean flow time, ideal time of machines, mean lateness of job. These are the basic criteria what we will be What has to be calculated or what has to be predicted. Mean tardiness of job, type of tardy jobs, mean queue time, mean time of jobs in the system. The solution procedure depends on the following factors: the number of jobs to be scheduled, number of machines in the machine shop, type of manufacturing facility, whether it is shop floor or flow shop or job shop, manner in which job arrives at the facility, it is static or dynamic, criteria by which scheduling alternatives are to be evaluated. Scheduling rules: easiest, earliest due date, that is EDD. In this rule, the job which has earliest due date is sequenced first for processing on machine. Job with next early due date is placed second in sequence for processing, and so on. All the jobs are sequenced for processing. This scheduling rule performs well with respect to minimizing percentages of job past due dates, minimizing the maximum amount of time of a job is late. Performs poorly with respect to job flow time, work in process inventory, and machine utilization. First come, first serve, FCFS. Quite simply, the job that arrives first on the shop floor is the one that has to be processed first. A variant, first come, first serve, bases the decision on the order in which the job orders are received. Rules of this type take no account of the current state of the shop on the actual due dates of the job, and jobs are processed in their arrival sequence. Shortest processing time, SPT. In this rule, the job with minimum processing time is scheduled first in the sequence. The job with next higher processing time is scheduled next, and so on, or since all the jobs are assigned. Job with highest processing time will be processed at the last. This rule is more convenient to apply for single machine scheduling. When two machines are there, Johnson rule is used for scheduling. The SPT scheduling rule performs well with respect to average job flow time, work in process inventory, minimizing percentages of job last due utilization. Performs poorly with respect to minimizing the maximum amount of time a job is late. The next part is longest processing time. In this rule, the job with longest processing time is placed first in the sequence. The performance of this rule is situation specific. Critical ratio, CR. It is the ratio to the difference of due date minus due days upon total shop time remaining. Job with minimum critical ratio is sequenced first. Performs well when we are concerned with global operation of a system or work centers. Now we will discuss a problem which is five sheet metal jobs are waiting to be assigned at work center. Their processing time in days and due dates are given. We have to calculate the processing time according EDD, FCFS, SPT, LPT, and CR. All ratios what we have discussed will be included in this problem. As far as EDD sequencing rule, the job which has earliest due date is sequenced first for the processing of the machine. Similarly, from the problem we see that we will find it out B, A, D, C, E. Respective values will be transformed accordingly: due dates, completion time, flow time, and tardiness. All these values are calculated accordingly. Then mixed spend time is 28 days. Mean flow time comes out to be 13.6 days, and maximum tardiness is 5. We will and mean tardiness is 1.2 days. Average WIP is 2.42 times. We move on to FCFS sequencing rule. Here, A, B, C, D, E. Plan has changed. The job sequence has changed over here. Make plan 28 days. Mean flow is 15.4. Maximum tardiness is again 5 days. Mean tardiness 2.2. Average WIP 2.75. Now we take the third rule, that is your SPT sequencing rule. Here we get BDACE. All the values are calculated according to the past what we've discussed. Again, maximum tardiness is in job sequence. Job related to element E, that is 5. All values are calculated, and now we move on to LPT sequencing rule. Here the sequence has changed and it starts from ECADB. Big span is 28 days, mean flow is 20.6, maximum tardiness is 22 days. Now we will have a look of the four different methods what we have studied and how they are performed or evaluated. The table shows the SPT performs best with mean flow time and average WIP, while EDT performs best for mean tardiness. Different rules perform better under different objective functions. If the number of jobs and the number of machines M increases, the scheduling problem becomes more complex. In fact, no exact or optimum solution exists for sequencing problems with large and M. Now we move to N jobs on one machine case. The case when a number of jobs is to be processed on a single facility occurs quite often in practice, such as number of cars to be serviced in a service station, number of patients to be treated by a doctor, number of jobs request for a different terminal users to be executed by a computer, a number of different jobs to be machined on lathe, a number of broken down machines to be repaired by a service mechanic. In all such cases, we as human beings are used to the first come first service concept. This seems to be the almost universally accepted code for handling sequences at milk booths, post offices, banks, and almost everywhere we go. Shortest processing time rule. Sequencing the job in a way that the job with least processing time is picked up first, followed by the one with the next smallest processing time, and so on is referred to as SPT sequencing and achieves the following objectives simultaneously, such as minimizing mean lateness, minimizing mean lateness time, minimizing mean waiting time, and minimizing the mean number of tasks waiting as in process inventory. Now we consider 8 jobs with processing time, due dates, and importance ways as shown in the problem. We have to pick up the shortest processing time SPT rule. Here, the job with the least processing time is picked up first, followed by one with the next smallest time, and so on, till we have picked all the jobs. SPT achieves the following objectives: minimizing mean flow time, minimizing mean in process inventory, minimizing mean waiting time, and minimizing mean lateness. Now we will be arranging the jobs in the processing time in the ascending order. All the jobs have been processed. They have been placed accordingly as per the ascending order. So that is, it starts with job 4813726. And similarly, the processing time are placed down under them. And the importance wait time is also depicted. The SPT sequence is 4813726, resulting in the completion of these jobs at times 3, 6, 56 respectively, or this we are summing up. For time, we have to take sequence. For example, if ti for job 4 3 is 3 and for job 8 it is 3, then we have to take first 4 and then job 8, or the reverse. The mean flow time, it's summation of all divided by number of terms, which comes out to be 23.87, which is equivalent to 23.9 units. This is the plan how this will be depicted mathematically. The second picture over here depicts the time span. 8 number of tasks waiting as in process inventory during time 03 week. It's depicted on the graph. 7 for 7, it is 3 to 6. Similarly, all the values are calculated. Mean wait flow time. You have to multiply these numbers with the mean time. And this comes out to be 29. That means that the average in process inventory is multiplication of the process time into the sequence divided by total time, that is 56, which comes out to be 3.41. The waiting time for each job is calculated. For job 4, it is 0. Job 8, it is 3. Job 1, it is 6. Job 3, it is 11. The total sum comes out to be 135. And the mean waiting time as per the SPT rule is 135 divided by the 8, which comes out to be 16.87. Lateness of each job. That means lateness of job number 4 is calculated by the relation completion of job of I minus due date of job. So all this is calculated and we find it out. The numbers which are marked with red are having positive lateness in tardiness. So we will be calculating the mean lateness, which comes out to be minus 3.625 units. And similarly, the mean tardiness is calculated, which comes out to be 7.8. Number of tasks actually late are 4. That is job number 3 to 5, 6. Because these are number of tardy jobs. Maximum lateness is 22 units. Now we move to n jobs with 2 machine case. Consider the situation where n jobs has to be processed on 2 machines, that is M1 and M2. The processing time of all jobs on M1 and M2 are known and deterministic. It is required to find the sequence which minimizes the time to complete all jobs. Johnson developed an algorithm that can be used to obtain an optimal sequence. In such case, Johnson algorithm is summarized as: list all processing times of all jobs on machine M1 and M2. Scan through all processing times of all jobs. Locate the minimum processing time. If the minimum processing time is on M1, place the corresponding job first, as early as possible in the sequence. If it is for M2, place the corresponding job last, as late as possible in the sequence. Eliminate the assigned job already placed in the sequence as a result of the step 3 and repeat step 2 and 3 till all jobs are sequenced. Any ties in the processing time while applying step 3 are broken arbitrarily because they cannot affect the minimum elapsed time to complete all jobs. 6 jobs go first in machine 1 and then over 2. The order of the completion of the job has no significance. The following table gives the machine time in hours for 6 jobs on 2 machines. Find the sequence of the jobs that minimizes the total elapsed time to complete the job. Find the minimized time for completion of all the jobs by using Gantt chart or by any other method. We will find out the smallest time from this, whatever is the information is given here, we can see for time 3 for job number 4. Therefore, we will be providing job 4. It is on machine 2 on the last. Now, we are left with this. Similarly, we are going to follow the minimum time first, depending upon the position of the machine. After performing the various steps allocation, we find that the complete sequence of operations is 315624. Now we have to calculate the minimum elapsed time. This is the problem what originally was given to us, and in the center we can see the actual sequence. Now we will be shifting we will clubbing these two informations to calculate the ideal time of the machine. For job, we will start with job 3. Sequence will be 315624. Similarly, in time and out time will be calculated. And for machine 2, again the time in and time out will be calculated. In the last column, we will be seeing or we will be calculating for how much time machine 2 was ideal. So for the job number 3, it was 4, and for job number 4, it was 2. This is how the computer uses your Gantt chart. The sequence, the total ideal time on the machine 2 is 6 hours, and for machine 1, it is 3 hours. It has been calculated by the help of Gantt chart. Now, scheduling rules for job shop. Practical job shops are much more complicated as may have hundreds of machining centers and thousands of jobs. In such cases, resort to make to priority dispatching rules of sequencing job at each machine center. This can be applied both in static and dynamic job environment. Commonly specified priority dispatching rules are FCFS, first come, first serve. Select the job on the first come, first serve basis. Select the job with shortest processing time. Select the job with earliest due date. Slack. Slack is select the job with the minimum static slack, that is due date minus time of arrival at machine center. Fifth one is random. Select the job in random order. Pick any job to be performed. LRPT, that is select the job with the least remaining processing time. Seventh one is select the job with the minimum ratio of job slack to the time to that of operations remaining. LCFS, that is select the job on the last come first serve basis. DS, select the job with least dynamic slack, and select the job with the minimum ratio of dynamic slack to processing time. And we can see that there are 10 different ways of selecting a job to be performed. Now, we move to Unit 8, that is planning and control of projects. A project consists of interrelated activities. Networks will be used as visualization of these interrelationships. A successful implementation of the project will involve planning, coordination, and control of the activities constituting the project. Each project involves consumption of certain raw materials and use of certain resources. Some of the examples of projects are erection of a manufacturing plant, preventive maintenance of a chemical plant, launching of a space vehicle, and construction of a building, etc. These are some of the examples of projects. Some of the examples have been discussed. These projects have a large number of activities that can be successfully completed only if the various activities are properly planned, time schedules are prepared, resource allocated, and a proper control is exercised during the implementation. Project management essentially deals with these aspects of the project. Depending on the nature of the activity times, the project will get classified into two categories. Project in which activity time can be estimated with sufficient certainty. For example, building a house or erecting a plant. Second one is project in which there is a high degree of uncertainty about the activity types. For example, launching of a space vehicle, developing a new product, etc. Time management of the project is the first case that is usually done by using critical path method, what we call it as CPM. And the second case using program evaluation and review techniques, that is PERT. With this, we will be concluding today's session and we will be continuing further with this topic only because this has some mathematical calculations to be performed.